Hi, everyone, and welcome to session 2 of the 7th MOOC edition, the massively open online course for the University of Nicosia's Masters in Digital Currencies. Welcome, everyone. I hear we have a record turnout for this particular session or series of sessions, and it's a great pleasure to be restarting the MOOC. And welcome to all the new students, as well as I know there are a few of my former students who are taking the course again to learn some of the things we've updated since the last time. Bitcoin is a fast-changing area of computer science and technology. And so we keep adding new material to the coursework. And sometimes we have students who come back for a second run. So welcome all. And thank you for all of the many great questions you've sent to me for session. Now, if you would like to also remember ask questions in the chat window, in YouTube comments, and so we can keep getting live questions from the audience as we go through this. First question we have is from Roberto. Roberto asks, reviewing the material about mining on slide 20 and 21, the last step refers to the hash being reviewed against the desired pattern in order to arrive to the prize, the reward. How is this desired pattern defined and generated in the decentralized platform? Is the desired pattern somehow centralized and broadcast to each node? What are the inputs to build this desired pattern? Is there a new pattern created whenever a new block has been created, and does that change per block? Great questions. This is an area that many of our students find confusing, to say the least. It is the topic of mining, and it's not that easy to understand. So let's get our terms correct. First of all, the desired pattern is called the target, and the target defines the difficulty. And if a miner achieves, through the proof of work algorithm, a result that is less than the target, they are eligible to receive reward if the rest of the information in the block and the transactions are valid and can be validated through the consensus rules by everybody else. Now, how is the target defined? And how does it change? This is a great question, and it's an area of great confusion. So the target is basically a number, and that number has to be greater than the hash of the block. So it's simply a greater than, less than operator that is being used to compare against this desired pattern. The miners are mining by hashing the header of each block, and the hash they're producing, which looks like a long string of hexadecimal digits, that's usually how it's presented, hexadecimal digits, is essentially just a number, right? And so if you think of the hash as a number, then the target is another number. And the hash of a block has to be less than the target. Now, one way I like to think of this is that the target is like a limbo bar. And if you've ever seen Limbo, it's where you have to dance and pass underneath a bar. And the lower the bar gets, the harder it is to pass underneath it for every limbo dancer. So if the target is lowered, it's actually harder to find a number that's smaller than that target. So every time the target gets lower, the difficulty becomes greater because it's harder to find a number that fits underneath the target. And that's basically the process by which the target is compared to the block hash. So the target number is a number that defines the difficulty of the proof of work mining algorithm. And if you see the target number, what you notice immediately by looking at it is that the first few digits are zeros. And that's because while the number started as a very high number back in 2009, when Satoshi Nakamoto mined the very first block, that number has now become billions of times smaller. And that makes the calculation billions of times more difficult. And so as it becomes a smaller number, that means that the leading digits of that number are zeros. So if you think of, for example, let's take a big number, 1,000,000. What's smaller than that? Well, it's 999,999 is smaller than 1,000,000, but that can be written as 0.999,999. So there's a 0 in the front. And what's smaller than that? Well, 1,000 is smaller than that, and that can be written as 0.000,1,000, and that's smaller than 1,000,000. So as you can see, as we go down, there's a lot of zeros at the beginning of the number. And finding a number that's even smaller than that target gets more difficult the smaller the target. And so the hashing process that miners conduct is random. It's a process by which they use a random number, they produce a hash, and what comes out of the cryptographic hash function is a number that appears to be random. You can't predict what the number will be. And so how do you know if it's smaller? You can't predict whether it's going to be smaller than the target. And in order to find a number that is smaller than the target, you just have to keep trying again and again and again, pulling out these random numbers from the cryptographic hash function until one of them, just by sheer chance, is smaller than the target. The lower the target, the more hashing you have to do before you find one that is smaller than the target. And that's the process by which the mining reward is allocated through the proof of work algorithm. So going back to Roberta's question, is the desired pattern somehow centralized and broadcast to each node? No. Each node independently calculates what the target should be and adjusts it. It started with a specific number that was hard-coded in the software in January of 2009 with a Genesis block. Since then, every 2 weeks, we have a retargeting, as it's called. So every 2016 blocks, which is approximately 2 weeks, on the 2016th block exactly, every node in the network calculates a new target for that next block. So they do blocks 1 through 2015, and then they say, OK, the next block is going to be block 2016. Therefore, we have completed one retargeting period, and we need to recalculate independently what the target should be for block 2016 before it's mined. So what should that be? Well, let's look at the previous blocks and say, how long did those take? So we look at the previous 2016 blocks, and we say, it should take 20,160 minutes, because it's 10 minutes per block. Now, if we count how long it took to mine the previous 2016 blocks, and we find that it was less than 20,160 minutes, that means that we were finding blocks faster than we should be finding blocks, which means that the difficulty was not as high as it needs to be. It was too easy. As a result, the target needs to be lowered proportionately in order to make it more difficult. If, on the other hand, we're finding blocks and it's taking longer than 20,160 minutes to find 2016 blocks, that means it's too difficult, and we're finding blocks too slowly. And so the target is adjusted up to make it easier to find something that's less than the target. And that's done, again, proportionately. So if you take that formula, the formula is proportionally adjust the target up or down by exactly the ratio of how long it took to find the blocks over how long it should take to find the blocks, which is 20,160 minutes. And that proportionate adjustment is the same for every node. So even though the nodes are not communicating or coordinating in any way, they can all count how long it took to find the previous 2016 blocks. And that's the same number across all of the nodes, because they count it by looking at the time in the headers of the blocks. They can also all divide that number by 20,160 minutes, which is the same number. And they're going to arrive at the same exact result. And if they then multiply proportionately the target by that number, they're going to get a new target. And all of the nodes in the network, having calculated the same equation with the same inputs, will arrive at the same conclusion. So they will all independently figure out what the target should be for the next block, the 2017th block in the series. And then 2016 blocks later, they'll do it again. And they'll put the same inputs in the equation, and they'll get the same retargeting value across the entire network. So even though there's no synchronization because they're using the same inputs, they all arrive at exactly the same conclusion. And that becomes the consensus target. So even if another node is lying and says that they found a valid block, since all of the nodes know what the target should be for this period, this retargeting period, they will all check against what that target should be, and they will only accept a block that has actually been mined to that specification, where the block hash is less than the target. So to answer the second question, what are the inputs to build this desired pattern? It's the number of minutes it took to mine the previous 2016 blocks divided by the expected number of minutes, which is 20,160. And the next question by Roberto was, is there a new pattern created whenever a new block has been created? And does it change every block? No, it changes every retargeting period, which is every 2016 blocks, or approximately 2 weeks. Evangelos asks, from page 20, a Bitcoin user downloads a piece of software, for example, the Bitcoin Core client software. So Evangelos' question is, what if this downloaded software is infected and serves under Ingress? Who is responsible to distribute software if we are talking about a totally decentralized system? How can I understand if it will be the original client software? That's a great question, Evangelos. So first, let's look at how we deliver secure software to everyone who wants to use the Bitcoin Core software or any other version of the software, any other form of Bitcoin client. And then let's look at what happens if it's not the correct software. So first of all, Bitcoin is developed using an open source model. And that means that there's a collaborative development process that happens in a public system. And that development is happening on GitHub, which is a collaborative coding software platform. So developers from all around the world contribute changes to the code. Those are reviewed by thousands and thousands of people who each look at the code. And a group of about 150 developers who work on this in a very concentrated manner, some of them working full-time on this software, all review and offer their opinion on the code. There are some developers who, through experience and many years of working on this project, organize all of the changes into the latest version of the software. And they produce releases. And a release is simply a specific version which includes the changes in the code. Now, these have been reviewed, as we said, in source code by many, many developers from around the world. Now, when Bitcoin was developed, a new system for building software was developed called Gitian. In fact, this is an invention by the Bitcoin developers that is now used for secure software distribution across the world and across other platforms, not just Bitcoin. Gitian is a system whereby software can be built independently on multiple different platforms. And the results of the software build mechanism are deterministic. This is called a deterministic build, meaning that the Gitian system simulates the exact same platform across many, many different computers that build the software independently from the source code. And from a specific version of the source code, they produce a binary that can be built on, that can be executed on different platforms. Let's say, for example, 64-bit x86 processors for use on Windows or on Linux. And those builds have a fingerprint. What Gitian does is, by building the software independently on many different systems and then comparing the fingerprint, it can tell you if you are getting the exact same executable result as everybody else. And that becomes one of the release builds. These are published on websites such as bitcoin.org, bitcoincore.org, and other places where individual users, developers, miners, etc., can download executables. Of course, you could also download the source code, and using the Gitian system or just a traditional build mechanism, you can build the executable and see what is produced. If you know you have the right source code, then through building it on your own platform, on your own computer, you can get a trusted executable. So once you have the executable, you can also do a fingerprint on that executable, and you can compare that fingerprint to the published fingerprints, which are available on a number of different sites, and confirm that, in fact, you have built the exact same executable as everybody else, and you have the expected result. Now, this ensures that when people download either the executable or the source code, they have a very dependable chain that goes back to the developers and the very, very highly reviewed code that the developers are collaborating on. But of course, no process is perfect. What happens if your software has been compromised? Well, here's the other thing. If you have software that is compromised, the biggest risk is actually to your own individual wallet on that software. So if you had, for example, downloaded a Bitcoin Core software that had malware installed in it, that will endanger your system. And if you haven't checked the fingerprints, and if you haven't used a deterministic build, or if you didn't download the software from a reputable source, you may download infected software. The thing that is most at risk there is your funds. So if you put money into a wallet on a system that has a virus, a malware, some form of malware, then you're very likely to lose your money. That's what the virus is going to target. But it doesn't actually pose a threat to the rest of the Bitcoin system. And the reason for that is because on the Bitcoin network, no node trusts any other node. It is assumed that your node, when it's communicating with other nodes on the network, it assumes that all of the other nodes cannot be trusted. And it doesn't take any of the data that is sent to it at face value. It doesn't assume that the data is correct. Every Bitcoin node independently validates all of the transactions, blocks, and forms its own authoritative opinion as to whether the nodes it's connected to are telling it the truth or not. If it finds nodes that are consistently lying to it, sending it wrong transactions or invalid blocks, it disconnects from those nodes and stops talking to them. So every node has this defensive mechanism where it doesn't trust any other node on the network. And it validates for its own authoritative perspective the transactions, the blocks, all the way back to the Genesis block. As a result, you don't need to trust that other software is doing what it's supposed to do. You don't trust that other software is doing what it's supposed to do. You validate yourself, or rather, your computer node validates everything itself. So yes, we can have malicious software introduced into Bitcoin. It's hard to do because of this deterministic build process, because you can essentially evaluate a chain of custody that goes from the developer source code that's widely reviewed all the way to the executable. But even if you don't validate that, the risk that that poses is primarily to your own funds and your own machine, because no other node on the network will trust you. By default, we don't trust other systems. The trustless nature of Bitcoin, the decentralized nature of Bitcoin, is because it doesn't trust any other nodes on the network. Andreas asks, if mining is for preventing miners from double spending their own transactions, why not simply flag their transactions and check them regularly? Well, Andreas, the mining is not for preventing miners from double spending. It's for preventing anyone from double spending transactions. Furthermore, even if it was just about miners, you can't flag which transactions are produced by miners, because you can't tell which transactions are produced by miners versus somebody else. There's no way to know who is a miner and who is not a miner on the system. Nodes operate under this cloak of anonymity, so you can't tell who is a miner on the Bitcoin network. And you certainly can't tell where a transaction came from and who mined it or who produced it, so as to be able to discern. Roy asks, Roy posted a tweet from June of 2013 that says ghash.io is now at 52% hash rate. And this can cause issues. So the question from Roy is, did someone find a way to prevent this from happening? Well, yes, in fact, Roy, that particular tweet was misstating the actual hash rate of ghash.io, which had not reached 52%. But in any case, What happened is that very quickly the hash rate changed because miners abandoned ghash.io so as to remove their hashing power from that pool. At times, various pools jockeying for position entice miners to join them and participate with their hashing. But if it looks like any pool is achieving mining hashing power that is close to a dangerous level, miners generally tend to switch pools. We've seen this happen with a number of pools over time. And there's no real way to prevent this from happening, because that's the nature of the system. You can't control where miners will commit their mining power, how they'll collaborate to form pools, or who has the mining power. But in fact, because of the costs of creating the mining power as well as retaining enough power in the network is very, very high, the practical risk of attacks, 51% attacks as they're called, is very, very low. And over time, we've seen that the amount of hashing power that any one miner or mining pool has become more decentralized over time. Now, if you think about it, back in January of 2009, there was one miner, Satoshi, and Satoshi had near 100% of the mining power. And then gradually more and more miners joined, and the mining power was further distributed. Today, we have many different miners who have different varying percentages of the mining power. But the number of pools and the number of miners is greater than it ever was in the past. And mining is quite a decentralized operation. Of course, the risk always exists. But the economic incentives of mining means that even though a 51% attack may become theoretically possible by any one miner, the problem is that by executing such attack, they get very little benefit, but they end up damaging Bitcoin in such a way that they lose all of the investment in mining equipment that they've bought, and all of the energy they've used up to that point. So the economic incentives actually disincentivize miners from, if you like, killing the goose that lays the golden eggs. Mark says, Bitcoin solves the Byzantine general's problem so long as honest, non-collaborating miners consist of at least 50% of the hashing power in the system. How do I know that at least 50% is an honest miner and not a traitor? Well, you don't know that. And the only way really to ensure that is to have mining power that is distributed amongst enough miners that they can't collude. Also, the system incentives that even if they do collude, the reward for breaking the system by doing a 51% attack is not worth destroying the system itself. Eric asks, how many miners are there out there? How many have successfully mined blocks so far? Where can I find this information? Are most miners traceable to IP addresses? Or are their IP addresses anonymized? Could someone create enough virtual lieutenants to bring down the general and replace him with a new one of the choice? Conduct a blockchain coup d'etat, as it were? That's a great question, Eric. So let's start from the beginning. How many miners are there out there? Well, it's actually very difficult to count. Unless miners identify either the pool or the mining system that they use by mining information into the header of the block, meaning that they put their signature in the block and self-identify, it's impossible really to tell who a miner is. You can maybe get some statistics by looking at the correlation to addresses that they use in the Coinbase. So every block has a Coinbase transaction which pays the rewards to the miner, and that has a miner's Bitcoin address. If they use the same Bitcoin address for every block they mine, you can correlate those blocks. But miners don't have to use the same Bitcoin address for every block. In fact, they can use a different Bitcoin address for every block they mine, and then you'd never be able to correlate them. We don't really know how many miners there are out there. We do see through the signatures in the block headers where mining pools self-identify. We do see how many mining pools there are. And there's about a dozen or so prominent mining pools, with 4 or 5 having the majority of the hashing power. Now, these mining pools are not necessarily also owners of mining equipment. In many cases, they are independent organizations, and the mining equipment belongs to others who are combining it in the mining pool. So miners and mining pools are not the same thing. We can identify mining pools. You can see statistics and a number of websites that show the distribution of hashing power on the Bitcoin network by mining pool. But again, this is self-identification, and the miners and mining pools can fail to identify, they can refuse to identify, or they can lie in their identification. And as a result, you can't really trace. The second question was, are most miners traceable to IP addresses, or are their IP addresses anonymized? They're not traceable to IP addresses. The Bitcoin network doesn't keep track of IP addresses because both transactions and blocks are propagated through the network through a mechanism called flooding. With flooding, every node sends everything it receives to all of the nodes it's connected to. If your node is connected to other nodes in the system and it receives a transaction or a block from another node, it has no idea if the node that it just received this transaction from is the first node where that transaction appeared, the originator, if you like, or if it's the node that's mined that block, or if it's a node that's simply relaying information from another node further down the chain. Every node only sees its immediate neighbors. It doesn't know where the information is originating. It just sees that it's coming from its neighbors. And the neighbors may simply be relaying information. When your node relays that information to the next node doesn't know if you're the miner or the originator of that transaction, or if you simply received it from somewhere else. And as a result, it's actually very difficult to track IP addresses, because you would have to be able to monitor all of the connections between all of the different nodes on the Bitcoin network. Now, there are certain organizations that can probably do this. Intelligence agencies can probably monitor a very large percentage of the various nodes on the Bitcoin network. But the Bitcoin network also uses various cryptographically secured protocols, such as Tor, the onion router, in order to route traffic. And if a miner or someone who's creating transactions is on the Tor network and their node is communicating only by Tor, again, it's very difficult to trace where transactions and blocks are coming from. And finally, the most important question you asked, Eric: could someone create enough virtual lieutenants to bring down the general, replace him with a new one of their choice, conduct a blockchain coup d'etat, as it were? This is a really critical question. This question you're asking refers to something we call a Sybil attack in security systems. A Sybil attack is where you create a lot of fake nodes that pretend to be real. Like, for example, let's say you want to persuade people that your opinion is very popular when it isn't, so you create a lot of accounts on Facebook, and they're all controlled by you, and they all pretend to have the same opinion. And people looking at that may think that there are a lot of people who hold this opinion, when in fact all of these accounts are connected and controlled by a single individual. That's called a Sybil attack. These types of attacks are called sock puppets sometimes. And the key there is that you can have one person or one actor create a whole number of fake accounts or virtual accounts. Bitcoin directly solves the Sybil attack problem, and it's the only system really that solves this as part of solving the Byzantine generals problem. By solving the Sybil attack problem by requiring each node, whether it's controlled by one entity or not, to produce proof of work. So you can create a lot of fake systems, but if you only have a certain amount of mining power and you create a lot of fake systems, all you're doing is you're taking all of your mining power and you're splitting it among many, many, many systems. And that doesn't do anything for you, because it just ends up diluting the mining power that each system can bring to bear. And in any case, identities don't matter. The only thing that matters in the Bitcoin network is the cumulative amount of hashing that you bring to bear to the network. So the number of votes you get do not increase when you have more nodes running. They only increase, in terms of the mining system at least, when you have more hashing power. Whether you do that through one node or several doesn't really matter. So can you create enough virtual lieutenants? Only if you buy enough hardware and spend enough electricity in order to power those lieutenants to bring down the general. And that's exactly the power of the Bitcoin consensus algorithm. Evangelos asks, as 15.2 million Bitcoins have already been mined, can one say that mining was profitable during the first years of Bitcoin's life, but mining is not profitable anymore? What kind of incentive would someone have to start mining when the rewards are so disproportional to a few years ago? Well, again, Evangelos, the profitability depends on a number of different factors, including the difficulty, which depends on how many other participants are trying to mine and how much hashing power they're bringing to bear. Mining is profitable. It's only marginally profitable at any point in time, and the proof of that is in the self-adjusting algorithm. Let's consider what happens if mining is no longer profitable. So if you are running a mining system and you can no longer make a profit, and therefore the amount of electricity you are spending costs more than the amount of reward that you are gaining through Bitcoin, what do? After a while, not being able to support this operation, you turn off your mining equipment. You no longer waste electricity trying to mine on an unprofitable system. When you turn off your mining equipment because it's no longer profitable for you to mine, what that does is it reduces the total amount of hashing power available to the network, which slows down the mining, meaning that blocks come out less often. And as a result, after 2 weeks, 2016 blocks, if the reduction in mining power is significant, there'll be a retargeting adjustment to make mining more easy to account for the reduced hashing power available to the network. As it becomes more easy, that makes it more profitable for everybody else who continue to mine. So by removing miners that are no longer profitable because their equipment is old, or perhaps because their energy is too expensive, the system self-adjusts through a market mechanism and becomes profitable for everybody else, slightly more profitable for everybody else. At the same time, if it's very profitable to mine, maybe you buy more mining equipment so you can generate more profit, and therefore you increase the amount of hashing power, which causes the difficulty to go up at the next retargeting, which makes it slightly less profitable for everybody. And this competition, as it's been going on since 2009, ensures that Bitcoin mining is always marginally profitable for the most efficiently operating miners with the most efficiently operating equipment, meaning the equipment that produces the most hashes per watt of electricity consumed, and the most efficient electricity price that they can find, meaning that the cost of electricity in the region where they are mining or from the source that they are using for electricity is lower than everybody else. So some miners will be profitable, and the miners that are not profitable get pushed out of the system because they're not profitable. This is a competition ensures that the market price discovery, if you like, of what is profitable for miners continuously adjusts every 2 weeks. So mining is profitable. However, it's only profitable if you invest in equipment that you can then defray over a period of time. That involves risk. It involves operating risk. You have to be very efficient in your operations. So it's only profitable today for miners that use highly efficient 16-nanometer manufactured application-specific integrated circuits with very high energy efficiency, located near energy sources that are low cost, and operate their systems very efficiently. For everybody else, it's not very profitable, and so they go out of business pretty quickly. John asks, while I understand that the computing power used to generate the proof of work derives value from the very fact that it secures the Bitcoin blockchain, I was wondering if there are any workable solutions for diverting that computer power for bonus value creation, tackling problems requiring big computing powers. Are applications like protein folding or finding sets of primes workable, or anything else workable in this space? John, yes. In fact, there have been a number of systems that attempted to exploit the mining algorithm, the consensus algorithm, to do things that people consider useful, such as protein folding or finding primes, etc. However, Bitcoin doesn't do that. Bitcoin uses an algorithm whose only use is for Bitcoin, really, and has no other practical use other than proving to the rest of the world that the miners have committed a certain amount of energy and therefore expenditure to back the security of the network. It's essentially the promise each miner makes. Here is a block. I have validated all of the transactions according to the consensus rules. I swear this under penalty of losing the energy that I have put in, and here is the proof of work demonstrating my commitment to securing and validating these transactions and obeying the consensus rules. That promise is in the form of energy consumed for the proof of work algorithm. Part of the problem with doing something else, something that other people might consider useful, is that that splits the reward. It means that the miners have two reasons for which they're mining. One is to secure the network, and the other is to produce protein folding signatures or large primes. So what happens if the production of primes becomes more valuable than the Bitcoin security? What happens if there's a disruption in that network? Let's say, for example, suddenly we find a new application for specific types of protein folding or specific types of prime numbers that make it extremely valuable to produce these numbers or these proteins. Well, the problem with that, of course, is at that point, it's no longer worthwhile doing the security on the Bitcoin blockchain. It's only worthwhile using that equipment to doing the protein folding. Or rather, it's more worthwhile to do the secondary function than it is to do the primary function. And then Bitcoin security ceases being the primary function, at which point you can no longer trust the promise. And the promise being, I committed this energy to prove that I did the security of validating the transactions. If you can't trust that promise, then Bitcoin securities fail. The whole idea of only doing this to secure Bitcoin is that you can trust that promise. It has no other incentive. There is no other reason you would be doing this calculation other than proving your commitment to doing the security of validating the transactions correctly. And so Bitcoin's mining is useful. It's useful in proving the security of the Bitcoin network. And the more energy that is committed to proving that security, the more secure the network is, and the harder it is to attack or compromise the security of the Bitcoin network. Bitcoin's proof of work algorithm produces useful work. It produces the security that backs a global currency worth almost $15 billion. And it produces the security that ensures that that global currency cannot be attacked by any actor, however large they may be, without colluding and investing a lot of money in hardware and energy. And that becomes very difficult the more energy and the more hardware that backs Bitcoin's security. That is the useful application of Bitcoin's mining. And we only have one because we want that to always be the dominant use of Bitcoin's mining and never become second place to something else. Lewis asks, I have still not found information about where the balance of a specific address is stored that is in terms of the amount of Bitcoins it holds. How does the network ensure that a fraudulent user can't alter that amount? Lewis, the reason you can't find where the balance is stored is because the balance is not stored. What is stored is a series of transactions that have credited a specific value of Bitcoin towards a specific address. And the outputs of those transactions are called transaction outputs, or TXO. And if they are unspent, they're called unspent transaction outputs, or UTXO. And those are the fundamental units that are stored in the blockchain. So when you see a wallet that shows you a balance, that's an artificial number. Bitcoin doesn't actually store the balance. Your wallet has to go through, scan the blockchain, find every transaction that paid a certain value to a specific address, the address of your wallet, or several addresses that your wallet controls, and count up all of the transaction outputs, add up all of the values that have been paid towards that address, see which ones remain unspent, and the sum of the unspent transaction output values is your balance, and that's displayed on the screen. Why can't a fraudulent user change that? Simply because they cannot go back and modify the transactions that occurred in the past and change the value of the outputs of those transactions, because those transactions were validated, included in a block, mined with proof of work, and included in a chain that has become unalterable, immutable, by the application of several more blocks, building on top of that proof of work, and creating essentially a monument of proof of work that strengthens the accuracy of that information the more blocks elapse. After 6 blocks or 6 confirmations, it becomes so difficult to revise that information, even if the entire network was colluding, and it costs so much in expended energy, that most applications consider that amount to be secure. So the network ensures that users cannot modify the balance, because the balance only exists in the form of transactions, the transaction outputs. And those transactions have been recorded in the immutable blockchain. Osita asks, is it possible to develop an algorithm for guessing a nonce, which will fast-track solving the Bitcoin challenge by a miner? Could that be related to the recent shattering of SHA-1? Yes, that's an excellent question, Osita. In fact, yes, there is the possibility of creating a shortcut that allows you to predict the value that is required in a nonce in order to produce proof of work of a specific target. That would involve breaking, shattering, if you like, SHA-256. SHA-1 was recently shattered, as the popular expression goes, meaning that the SHA-1 cryptographic hashing algorithm, has been compromised in such a way that you can create a collision. That means that you can produce a specific pre-image to the cryptographic hash algorithm, which will result in a desired hash as its output. That ability to produce a desired hash from a pre-image that is identical perhaps to another, to the fingerprint of another pre-image, a collision as it's called, is a fatal flaw. And if you discover a fatal flaw in an algorithm, as has been discovered in SHA-1, then that algorithm is no longer suitable as a cryptographic hash algorithm. You cannot use it for the purpose of fingerprinting documents. You cannot use it for the purpose of, for example, fingerprinting digital keys, certificates, SSL, cryptographic keys, and the integrity of messages that are validated through cryptographic hash algorithms. And SHA-1 can no longer be used for those purposes because it has been fatally compromised. However, Bitcoin mining uses SHA-256. SHA-256 is enormously more complicated to compromise. So every cryptographic algorithm has a certain shelf life. On average, 20 to 25 years before a cryptographic algorithm can no longer be considered secure. Depending on the cryptographic algorithm, the shelf life, if you like, for that algorithm may be greater or lesser. Some have weaknesses that are discovered, which shorten the shelf life, make it easier to find a shortcut to compromise. Most cryptographic algorithms are based on some kind of trapdoor function, a mathematical function that has no shortcut, where the amount of computation required to go one way through the algorithm versus to go the opposite way is immense. And as long as you can't find a shortcut, that algorithm is secure to a certain amount of computation. If there is no shortcut, SHA-256 will continue to be secure for decades and decades longer. If a compromise is found, or some kind of shortcut, that doesn't mean it's fatal. It doesn't necessarily immediately invalidate the algorithm. It may weaken it by a certain percentage. So it may make it twice as easy to find a suitable hash, or maybe 4 times as easy to find a suitable hash. And that would certainly by weakening the algorithm, shorten its shelf life, because as computing power continues to develop, that means that at some point it would be viable to break the algorithm, essentially. Now, so far, there is no shortcut that has been discovered for SHA-256. And one of the reasons we know that is because Bitcoin represents effectively a giant global piñata stuffed with $15 billion that if you bash with the right shortcut for SHA-256, you can break it open and collect $15 billion. Or you can collect some percentage of that before the value collapses catastrophically by breaking the piñata. Essentially, it's a honeypot. Bitcoin represents a global test that tells us that SHA-256 is secure. How do you know SHA-256 is secure? Bitcoin is worth 15 billion, and no one's cracked it yet. Now, at some point, it may become obvious that SHA-256 is no longer secure, or it's reaching the end of its life, or we find new vectors that perhaps in a decade or a longer period of time may make it insecure. At that point, the Bitcoin developers, in collaboration with the rest of the community, would have to work to modify the proof-of-work algorithm and replace it with a more modern algorithm. And certainly, that would be a very big undertaking. So that's how we know that there is no shortcut to SHA-256. And if Bitcoin was using SHA-1, then some miner out there today would have been able to break it. And very quickly, every miner out there would have been able to break it, at which point it's no longer useful as a mining algorithm. Let's see if we have any questions from the chat rooms and from the live session. That completes most of the questions I had from the forums. And just a quick check here. Very good. Here's one question from the forums. On what basis does my node connect to other nodes? Can I be cheated and connected to dishonest nodes? That's a great question. Your node connects to other nodes by a process that starts out by discovering some of the well-known nodes, which are called seeds, and then branching out and finding other nodes by exploration. And it does so randomly by making its own decisions about who it connects to. And then it doesn't trust these other nodes. As long as it can validate, it only trusts, these other nodes as long as it can validate the transactions and blocks that it receives from them. So every node has to constantly prove its loyalty by sending good transactions and blocks. And the moment a node that we're connected to stops sending us valid transaction blocks and starts sending us incorrect transactions and blocks, our nodes will disconnect from them and ban them as being dishonest. So nodes will, once they've discovered a few nodes that they trust, if you shut down your nodes and restart it, it's going to then connect to those trusted nodes again randomly. Try them out. See if they're still online. When it connects to them, it's also going to ask them, do you know any honest nodes? And they're going to reply with a list of other nodes that they know. This is the ADDR message on the Bitcoin peer-to-peer network protocol, ADDR, which stands for address. So a node will ask, ADDR, do you have any addresses for me? And the other node will respond and say, well, I know these honest nodes that I've been talking to for a while that have proven to be honest. And so your node will learn from the ones it knows. It will learn about more honest nodes, and it will connect to them randomly and then test them, and then ask them for honest nodes, et cetera, et cetera. So each node does this so that it can constantly maintain a healthy network of honest nodes. It tests all of these nodes, and nodes that are dishonest very quickly get disconnected from the network. Second question, is Bitcoin secure without a block reward and without a backlog in transactions? Will it eventually come down to either a limited block size or the need for inflation? That's a great question. The answer is really simple. Bitcoin is not secure. Without a block reward and without a backlog of transactions, we can't maintain decentralization. You can make a system like Bitcoin that does not require a block reward and does not have a backlog of transactions. All you have to do is find one party that can be trusted with maintaining the integrity of that system and make it completely centralized. We have systems like that. The banking system is a system like that. The SWIFT wire transfer system is a system like that. The New York Stock Exchange is a system like that. It only works if you trust SWIFT, if you trust the New York Stock Exchange, if you trust the bank to maintain the integrity of the transactions. And the weakness of these systems is that you have to trust a centralized actor, and that actor has enormous power and control over the entire system. So is Bitcoin secure without a block reward? It may be secure, but it won't be decentralized. Decentralized Bitcoin can only be secured with a block reward. Decentralized Bitcoin can only be secured if there is a transaction backlog, and the transaction backlog is because we have to ensure that only transactions that have paid adequate fee are included in blocks to ensure the decentralization of the network. If you just include every transaction out there that people create without consideration for fee, including as many free transactions as anyone is able to create, then you create enormous blocks. Enormous blocks require enormous bandwidth. They require enormous storage. And then only those who have enormous bandwidth, enormous storage, can participate in mining and running nodes, which means that the network becomes gradually more and more centralized until it is no longer a decentralized network like Bitcoin. So as a result, the backlog of transactions, and keep in mind, the backlog you see in the mempool is only a fraction of the backlog of transactions that actually exists. If you look at the mempool at the moment, what you're looking at is the transactions that were propagated because they exceeded the minimum threshold of fee required for relay. Who knows how many thousands and thousands and thousands of transactions were never relayed because the very first node that received them said, nope, I won't relay this. It doesn't pay enough fee. Minimum relay fee, I believe, is at the 10th of a millibit right now, which means that there may be thousands, hundreds of thousands, gigabytes and gigabytes of transactions with a fee less than that, with a fee less than, for example, 10 satoshis per byte, that never get relayed and never get added to the mempool. And then there's ones that are marginal. They're just enough fee to get relayed and added to the mempool, but then not enough to get mined in the current capacity of the Bitcoin network. And as a result, they create a backlog in the mempool. That's because if every transaction, whether it has a fee or not, was mined into the network would become massive and centralized very, very quickly. Is Bitcoin an incentive for the development of the quantum computer? I mean, being a possible threat to the network security, doesn't this accelerate the race towards it? Do you think miners think about this at all? Great question. Bitcoin is a honeypot. Effectively, it provides a bounty for anyone who produces any type of technology, whether it's a SHA-256 collision that we were talking about before, whether it's a quantum computing shortcut to SHA, or to elliptic curve digital signature algorithms that may result in being able to compromise some or part of Bitcoin, or being able to weaken Bitcoin. Certainly that provides an incentive. So you can think of Bitcoin as a test. Bitcoin tells us SHA-256 is secure. ECDSA is secure today from any and all threats. And how do we know that? It's because it continues to maintain security over $15 billion. Therefore, we can assume that these technologies have not been compromised yet. Does it accelerate the development of these things? Probably, although I think most of the really interesting developments in quantum computing can deliver a far, far greater reward for those who develop these technologies than simply the $15 billion that's tied up in Bitcoin, because quantum computing has very broad applications. Furthermore, the application of quantum computing to Bitcoin is marginal at best. First of all, SHA-256 and cryptographic hash algorithms like SHA are not particularly easy to optimize using quantum algorithms. elliptic curve digital signature algorithm and elliptic curve cryptography can be massively optimized with quantum computing, and quantum algorithms for doing elliptic curve factoring, in fact, do exist, and they will allow someone to break elliptic curve cryptography eventually and factor large elliptic prime fields, elliptic curve fields. For now, the elliptic curves that we use are far greater in the field that's used for the elliptic curve is far greater than any quantum computer can factor. So that's not a risk. At some point, it would become a risk. And at that point, you have very, very powerful quantum computers that can do that. And then the security of elliptic curve cryptography is no longer good. But elliptic curve cryptography can be replaced in Bitcoin by other algorithms. And because of the mechanism by which public keys are not demonstrated to the network until an amount is spent, if you follow the best practice of only using an address once for each transaction, then the only time your public key is demonstrated to the network, shown to the network, is when you've spent the amount of Bitcoin that was in that address. And therefore, even if you were able to break public keys, as used in elliptic curve cryptography, you wouldn't have any Bitcoin to get behind it because it was only ever used once. Bitcoin addresses, of course, are secured through two applications of hashing algorithms, SHA-256 and RIPE MD160. And those are far less susceptible, those two algorithms, as well as the mining algorithm on SHA-256 as well, are far less susceptible to quantum algorithm optimizations, as far as we know. And therefore, it may be a very long time until quantum cryptography has any impact on Bitcoin. And of course, the other thing to consider is it also depends on how broadly quantum cryptography is available. If quantum computing is available. If quantum computing is broadly available, then just as much as you can make better algorithms for cracking keys, you can also make better algorithms for making keys. You can make quantum mining algorithms. You can make quantum cryptography algorithms. So if quantum computing is broadly available, then I can use quantum computing to do encryption and digital signatures and mining. And then the fact that others have quantum computing doesn't make any difference because my cryptography, my digital signatures, and my mining algorithm are just as secure. So really, it's about the unequal availability of quantum cryptography, which is a whole other topic, perhaps for another session. And with that, we've reached the end of our time. Thank you so much for participating in session 2, I believe. Yes, session 2 of the Massively Open online course for the Masters in Digital Currencies for the University of Nicosia. This is Andreas Antonopoulos. It's been a pleasure answering your questions. Don't forget, we'll be talking again next week. And until then, please study the material, ask great questions, discuss it amongst yourselves, and I'll see you all next week. Thank you.